for the very warm introduction. So let us now turn the focus from me to Dr. Grobner. Okay? So this is a lecture where I am going to introduce a rather weird sounding thing. And is there anyone who has heard this concept called Grobner basis? Good. Oh, you have? Oh. So in this case, I actually assume that no one would even know the name, so I will start from the very beginning. So this is a concept from algebra, and there are quite a few applications of that concept in statistics. There are some research papers, and there is one collection of books. There is one collection of papers where they describe various applications of algebra to statistics. And there are quite a few papers on application of Grobner basis to various aspects of statistics. The thing is not very difficult, but at least in India, it is not at all well known. And I think that if you start understanding the concept, many people can do fruitful work on that. So I am trying to introduce the concept. The particular application that I will be talking about is nothing very profound. It is not one of the greatest applications of Grobner basis or anything. Just something which gives you a friendly hands-on introduction to the subject. So let's start. Good. So I will start with a very simple problem, a very standard problem. So you all know about fingerprints. We know that fingerprints are some indelible things. You cannot change it. So you can recognize people using fingerprints. So there are different types of fingerprints that the experts can recognize. And here is a simple example of that. That pattern is a whorl pattern. Do I have whorl pattern? No, I do not have whorl pattern. And this is a pattern which is a no whorl pattern. So there are typically 4 or 5 major categories of fingerprints. Here I have classified them into 2 parts, whorl and no whorl. And we are typically interested in questions like, is this pattern hereditary? So if my parents have whorl pattern, is it more likely that I will also have whorl pattern, or the patterns keep on flipping? We want to know that. That's a very standard question. And how do you find answer to such a question? Of course, you use statistics, and for that, you collect data. So here is a typical data set that some people collected, and you can get the source, etc., from that website. So it was collected in the following way. Some 207 families were interviewed, and the fingerprint pattern of the mother was found out. NW stands for no whorl, and for the child, whether it is whorl or no whorl. So you have lots of different cases, 4 different types: no whorl, whorl, and no whorl, etc., etc., etc. So all the 4 patterns are just showing up. And there are total 207 such families were interviewed. Now, just by looking at such a table, it is very difficult to get any meaningful information. So we naturally represent this as what is called a contingency table. So here we have a 2 by 2 table. I have got 207 families. Out of them, 162 mothers did not have whorl. 45 had whorls, and out of the children, 164 and 43. So I can see that 10 families had whorl both for the mother and the child, and actually most of them do not have any whorl because there are some 5 or 6 categories, some 4 or 5 categories. I am considering only whorl, and all the other categories are lumped together into no whorl. So that's why the number is pretty large. And the standard question is there any association between this variable, a child having whorl, and this variable, a mother having whorl? And what is the very standard way of doing it? You will go for a chi-square test. And what's the chi-square test? Let's quickly recall. You find out the observed frequencies. These are the observed frequencies. I call them Nij's. So it is N11, N12, N21, N22, etc. And then you also find out the expected frequencies, that is, had there been no association between child and mother, what would you expect? That formula is this. Mij is ni dot n dot j by n. Let me very quickly explain. That's a very standard thing. Suppose I want to find out what is the expected number that I will expect if there is no association. You just take this number, the row sum, the corresponding column sum, multiply and divide by 207. So I am not explaining it any further because I guess most of us are already familiar with this. So basically our aim is to compare these nij's with the mij's. If they are pretty close, we will say that it seems that there is not much association, and if they are far apart, then we will say that there is some association. And this is the standard chi-square statistic by which you will measure whether the nij's differ a lot from the mij's. That is kind of a distance measure that you can do. It is very easy to guess that if this number is small, then you will say that heredity has no effect. So whether the mother has war really does not have anything to do with whether the child has war. So this should be small enough if there is no heredity effect. The question is, the question of calibration, how small is small enough? Because I cannot expect that this will be exactly equal to 0, in which case nij will be exactly equal to mij. That we cannot expect because of random fluctuation. So how small is small enough? That is the problem of calibration. And this is typically answered by using the so-called chi-square distribution. In absence of any actual association, we are told during our undergraduate days that statistic T follows chi-square with degrees of freedom 1, whatever. So it's some standard complicated formula. You get lots of tables and lots of software programs that will compute stuff for you. And then you compare. So typically, this is how the density will look like. You find out what the particular value that you get. Suppose I get this particular value. It happens to be 0.04 for the table that I showed. And it seems that, yes, in this case, this value is very much in accord with this chi-square 1 distribution, and you will say that there does not seem to be any significant association between mother and child's finger patterns. Good. It's a very standard thing. Unfortunately, this thing requires certain assumptions which are not always satisfied in real life. One assumption is you must have a large sample size, and the other assumption is none of those expected frequencies should be too small. Certain textbooks try to say things like no expected frequency should be less than 5. This number 5 is just looks like a magic number. It's just a rule of thumb. But the idea is if some expected frequency is too small, then that chi-square approximation is bad. And in real life, it is quite possible that for a particular data set, these assumptions are not satisfied. What to do then? Of course, the idea of using a chi-square statistic seems to be quite reasonable. You are trying to find out what are the expected thing and what you have actually observed, and you want to see how far the expected thing is from the observed thing. That is the reasonable thing. But that chi-square distribution, that magic distribution, will not work. So what should I do then? So what to do if some expected frequency, say, is below 5 or very small? Now there is a standard technique by which you can tackle this. In this particular case, there is a standard technique by which you can tackle this. So let me just quickly tell you. This is the technique of randomization. I have seen that there are many people who are not really actually comfortable with the idea of randomization, but it's a powerful technique. So this is how we do it. Okay, so I have got 207 families. Each family has a mother and a child. So what I do is I make all the mothers stand in a row. So all the mothers are standing and the children are standing beside them. So I have got a row of mothers and a row of children. This pairing is done by nature. So there is some genetic linkage between this mother and this child, and I want to know whether that linkage is of any use or not so far as predicting fingerprints go. So what I will do is I will consider these children, 164 of them without whorl and 43 with whorl. All these children are standing. I will just reshuffle them. Keep the mother standing in the same row, in the same line without changing position, but take these children, randomly permute them. So I deliberately destroy any linkage between the mother and the child. So that, for example, right now I have a child without world. So after I do this, I just randomly shuffle same children. So the total number remains 164 and this remains 43. But now the matching, the pairing has changed. Since I have done it artificially with all permutations equally likely, I know that I have created a data set where there is no association. I have guaranteed that. And based on this, I will compute a chi-square value. This chi-square value is going to represent a situation where really there is no association. Because I played God, I created the table. And I will do it again and again. So this is the overall idea. I take all the mothers, 162 without world and 42 with world, all the mothers, arrange them in a line. Then I take all those children and arrange the children randomly. I construct the 2 by 2 table and compute that chi-square statistic based on that artificial table. I do these steps. So if I do this, I get one value of chi-square. This value is guaranteed to come from a situation where there is no association, because I have deliberately destroyed the association. I will now repeat this step, these things. I will keep the mothers fixed in their positions. I will keep on doing this again and again. So every time I will reshuffle the children and compute the chi-square values. If I do it n times, I will get n values of chi-square. All these things represent the situation where there is no association. Now I will compare, I will draw their histogram, and this histogram will play the role of the chi-square distribution. I know that this is the behavior that I expect of my statistic had there been no association. Now I can compare the chi-square that I got from the original table against this. For example, if I really carry this out, one can do this very easily using R, I get this type of histogram. So this is my approximate chi-square thing. And here I can again look at, well, 0.04 will be somewhere here, which means that again I accept the null hypothesis. This technique, a very powerful technique, does not rely on any assumptions like large sample, etc., or all expected frequencies must be at least 5. And this can be used for whatever test statistic you have in mind. Even if you have something completely ad hoc, you can do that again. So you just create your own data where there is no association, look at the behavior and check it. Now this method is a nice method. I am going to give one alternative to this method, which I must admit right at the beginning is inferior to this method for this particular example. But still I will use this example because that is the easiest way to introduce it. The method that I am going to mention using Grobner basis and all that is far more superior because it can be generalized to many more complicated situations. In this case, when you are just testing for association versus no association, this technique is better. So don't use the Grobner basis technique for this particular problem, but that can be generalized. But I will still use this example as a simple platform to showcase the various steps. So in this problem, what we did was the following. I had my 2 by 2 tables, and I wanted to generate a random 2 by 2 table under the assumption that there is no association. What I did in the randomization technique is I did not work with the 2 by 2 tables. I worked with the raw data. And the raw data means a table, mother, child, mother, child. And there is an enormous number of ways by which you can make the child pair up with the mothers. In fact, there are 207 factorial ways. I picked one at random. Every time I was shuffling the children, I was basically picking one such pairing at random, computing the corresponding table, and then finding out chi-square, etc. This has one little disadvantage. That is a huge set. So you are trying to sample from a set of 207 factorial. This obviously is much smaller. It's way smaller than that. This function is many to 1. That one is 207 factorial. You can compute it. It is not that easy to find out what is the total number of 2 by 2 tables such that the marginals will be that. It is not very difficult, but if it is something like m by n table, that itself is a pretty tricky problem. How to find the total number of m by n contingency tables such that they have fixed marginals, some given marginals, some given totals. So that is not a very simple problem. There, the distribution was uniform. We worked with the uniform distribution. We picked any one of them at random. I said, I am working under the null hypothesis of no association, meaning you can just pick the children randomly. That was easy. In this case, once you collapse things, this becomes some kind of a hypergeometric distribution. If you try to write it down, what is the probability that you will get this particular table? You can guess there will be factorial terms coming up. So how many cases such that these can be chosen in that way, etc. Lots of factorials will come up and it will look something like a hypergeometric distribution. Maybe pretty complicated if you are working with m by n tables. If it is just 2 by 2, it is the hypergeometric distribution. Otherwise, it's a pretty complicated thing. The technique that I am going to mention will work on this set. So again, it's the randomization technique, but you do not randomize on this set, you will randomize on this set. Advantage number 1, the set is much smaller. Advantage number 2, this will work for whatever arbitrary distribution that you have in mind. That technique worked because we worked with uniform distribution. If you have some more complicated model that you want to test, then that technique will just fail. You cannot generalize that. But this technique will work for anything. Whatever distribution you can write down, you can actually simulate from this set. And it can be generalized much further beyond just contingency tables. But we will stick to this example. So that is sort of the motivation, what we are going to do. So far, I have already finished 20 minutes. I have not even talked about Grobner basis. The time is going to come. So the technique that we are going to use is actually an example of Markov chain Monte Carlo. That's a buzzword. Everyone seems to be talking about Markov chain Monte Carlo. And for many people, it is a very complicated thing that Bayesians do, and you can write a lot of paper on them. But is it very practically useful? And not really. Okay. But no, it is a very standard and a simple thing. We have been using it right from the day of our childhood without knowing. That's one example of Markov chain Monte Carlo that all of us use. The main idea is you inject randomness bit by bit. In this sense, it is very much like iterative methods for solving equations. For example, if I ask you to solve an equation, in that case in school you do it just using certain analytic techniques. You just do manipulation and it becomes x equal to something phi of x, and you say I have solved it. But if I ask you to solve something like x equal to cos x, howsoever you manipulate, you can never bring x on one side and constant on the other side. Then we use methods like Newton-Raphson. These are iterative methods. They gradually approach the correct answer step by step, produce an approximate answer. So when you hear about them for the first time, you cringe that, no, this cannot be a good method. This is not exact. This is approximate. But then we know that they are actually very powerful. Similarly, Markov chain Monte Carlo adopts the same technique. When you want to generate random numbers, do not do it in a one step. Do it step by step. Now here is the example of MCMC that we have been familiar with right from our childhood. Suppose I want to take a deck of cards, and before playing, I want to ensure that it is perfectly mixed up. So all the 52 factorial permutations possible are equally likely. Here is a very simple way of doing it. You write down all the 52 factorial permutations on separate pieces of paper, 52 factorial pieces of paper. Good. Mix them up in a hat. You need a very big hat for that, and pick one at random. It is going to work, true. But we never do it like that. The way we do it is the following. Suppose I have got these 9 cards. Okay? And these come just fresh from the factory, so they are always in the correct order. You split it up into two parts, the top part and the bottom part. You take one of them in your left hand, the other in the right hand. This cutting itself has a little bit of randomness. You cut more or less in the middle, and then what do you do? Brrr, and you mix them up. So you mix them up. This injects a little bit of randomness. It is not completely random yet, because the interleaving of the cards, that is random. You do not know whether this is going to land first or that is going to land first. Still, it is not completely random, because you see, 1 must always be above 2. 2 must be above 3, and 3 must be above 4, and 4 must be above 5. These red things must still retain their orders. It is never possible that the top card drops first and the bottom card comes after that. However, the interleaving, that is random. You do not know whether 1 will come first or 6 will come first. So the blues are all still ordered, the reds are still ordered, but the relationship between blues and reds, that is random. So it is random to some extent. You have injected a little bit of randomness, but not completely. Okay, now what you do, you again cut this deck into two parts, again do it randomly. Suppose these things go in one hand, these go in the other hand, and again you go brrr, and you get something which is a little bit more random. So you are injecting randomness bit by bit, and all of us know if you do it a sufficiently large number of times, in that case, excuse me, the deck of cards gets pretty well mixed up. And there is some amount of research on that. It says that you have to do at least 7 shuffles before you can reasonably mix them up, etc., etc. But even intuitively, we understand that this is a reasonable procedure. Instead of randomizing all in one go, you make it a bit random, a bit more random, etc., etc., until it becomes quite random. That is the idea of Markov chain Monte Carlo. You inject randomness bit by bit. How you inject the randomness, that depends on how ambitious you want to go with the mathematics, but this is always the main idea, shuffling of cards. Now we are going to use this technique, but there are certain theorems that one needs to know, at least have an intuitive grasp of them, that I want to present as puzzles. So the puzzles are mainly to see that certain things are intuitive, so they are easy to remember, and certain things are counterintuitive, so you remember them specially. So here is puzzle 1. Suppose I have a map like this. So it's a city map, those are the roads and these are the junctions, and you start from some given vertex. Suppose I start from, say, here. It doesn't matter, but some fixed vertex that we know. And then what I do is, I do a Markov chain Monte Carlo. That is, at every step, I add a little randomness to my position in the following way. I pick any one of the edges, any one of the roads, here I have 3 roads, at random, 1/3 probability each, and just follow it. If I am here, suppose by random chance I come here. Then I have 4 roads, I can pick any one of them at random, 1/4 probability each, and follow it. Quite possible that I will again come back here. Then possibly I come here, then possibly I come here, go here. So you understand, at step 0, I was at a fixed vertex. I know that I will be here, no randomness. After step 1, you are at a random position, but still confined within these 3 things. It is not completely random all over the place. After the next step, you are likely to explore a little bit further, and you go on doing and doing and doing this at every step. Can you guess what will happen in the long run? You will be at some random vertex, true, but can you say anything about the probability? Will it be uniformly random? You are equally likely to be at any vertex, more likely to be at some vertex. What's the guess? Any guess? Yeah, that's a Markov chain, and I'm asking about the limiting distribution. What would one guess the limiting distribution should be? Uniform? Right, I just mentioned the transition matrix. This is the rule. Whenever you are at any one position, you will pick one of the edges at random. So 1/3, 1/3, 1/3. So if you just look at the transition matrix, all the entries, there are at most 4 entries, because there are at most 4 exits, and all those things have equal probability. So that's my transition matrix. I've completely described the transition matrix in terms of the map. What do you think? just intuitively. For example, if I say that everything is equally likely, you are as likely to be found, say after 1 million steps, you are as likely to be found here as there. Is there something which will make your mind revolt? Oh, no, that cannot be. So I'm not saying that try to think of theorems, anything. I'm trying to say that try to grasp it intuitively. If I say that all the things are equally likely, there should be something which should make you say, no, 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 that can't be. What should be the natural thing? Do you think that this is more likely or this is more likely? This is more likely. Why do you think so? Because it is more connected. Because you are picking things at random, you are more likely to spend times in those vertices where the degree is higher. Degree means number of incident things. For example, this is very close to the idea that Google uses for its page ranking algorithm, where these are the web pages and these are the links. And if someone is clicking randomly, then certain pages he will actually visit more and more often, because many, many links lead to those things. But of course, that involves some more complications, because there you cannot move just two-way. It's actually a directed thing. So you can guess that the vertices where the degree are higher are more likely to occur if you do it in a large number of times. For example, if you do it in Kolkata, if you are familiar with the map of Kolkata, in that case you will find that you are visiting Dharmatala more and more often, because almost all the bus routes actually converge there than in some exotic place. So intuitively we can guess that the probability is actually proportional to the degree. So the probability that you will be found here is exactly same as you will be found here, which will be exactly double that you will be found here. And you can prove it using just writing down the mathematics, but I want you to have that intuitive feel. And this is irrespective of the starting vertex. You start from here, you start from there, doesn't matter. If you play this game a large number of times, then eventually you will always be at one of these things according to that probability. So that is, of course, I could have presented it as a theorem with blah, 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 but I think this will give you a better hang of the thing. So here is puzzle number 2, which is just a little modification of puzzle number 1. Same thing, but now this comes in some disconnected parts. Again, the same story. You start from any given vertex. Suppose I start from here. And you follow an edge at random. You keep on doing this. What happens in the long run? From the first puzzle, the answer should be just obvious. What should it be? So suppose I start from here, then what is the chance that after a million steps I will be found here? 0. You'll never go there. So you'll be stuck inside that component. But inside that component, it is just like puzzle 1. So you'll have more chance being found here, because it is 3, less chance being found here, etc. So in this case, probability is still proportional to degree. However, you are stuck inside the part containing the starting vertex. Here, it is not independent of your starting position. This is going to be of crucial importance later. In terms of Markov chain, we call it an irreducible Markov chain, but we do not need all those terms here. The main idea is, if it comes in separate parts, you can never move from one part to another part. So things must be all connected. Okay, so far I have got a distribution which is, well, that is nice. It is proportional to the degrees, but that does not seem to be of much use. Why should I care about a distribution which is proportional to degrees? So here we try to modify things a little bit. So I do not want the limiting distribution to be proportional to degrees. So I want this fellow, this random thing, to move away from these high degree vertices. And if you are here, I want to keep them at the low degree vertices just to balance, such that they get less traffic and they get more traffic, so that hopefully things will balance out. And here is the scheme by which you can do this. Again, the same idea. You start from any given vertex, some fixed vertex. Now, try to move east, west, north, or south with equal probabilities. So I have got 4 directions. Pick one of the 4 directions at random, probability 1/4 each. Suppose I am standing here. I pick one of the 4 directions. Suppose the direction that I pick happens to be, say, north. Okay, I move north. Now again, I pick one of the 4 directions. Suppose I again pick north. Oops, I cannot move north. In which case, I remain there for that next minute. I again, after that minute is over, I again generate one of the 4 directions. Suppose I again pick north. Okay, I'm stuck. I'm stuck there for the second minute. I again generate. Now I get, say, east, and I move in this direction. And then possibly south. I move this direction, south again. If from here I try to move east, I cannot move east. So I remain stuck. So that is the scheme. So try to move east, west, north, or south with equal probabilities, not caring about whether you really can do it. And lose a turn if that is impossible. You cannot follow that chosen direction, and you go on doing it again and again. The aim here is that if you are in a very well-connected place, you will never remain stuck. You will always move out. If you are here, then if you choose east or west, you will be stuck. So whenever something has low degree, we are giving this random point some incentive to remain there. And whenever it is well connected, we are kind of giving him an incentive to leave that place. Based on this intuition, what do you expect will happen in the long run? Again, just from your gut feeling. It will not get stuck with any vertex with one edge because it will come here, okay, it will generate north, south, east, west, suppose north, stuck, 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 but sometime or other it is going to generate west and then it will come out. But it will stay a long time before it comes out, but eventually it is bound to come out. It cannot get stuck forever. But you are right. According to an earlier scheme, the probability of your coming here was very low. But here, once you come here, you will stay there for quite some time. Now, what do you think will be the limiting distribution? Guess, just guess. No theorem, nothing. It should be uniform. And indeed, you will now get equal probabilities. And this is a very useful result. What's the beauty of this? The beauty is you do not even need to know the entire map. Suppose it is an unknown city. You do not know anything about that other than the fact that it is completely connected. You know that the roads are north, south, east, or west. You do not know whether you can always move north, but it is north, south, east, or west, nothing other than that. And on a stormy night, you drop down at one of the vertices on a parachute. Then you can follow this prescription completely without knowing the entire map. And in the long run, you are guaranteed to be anywhere with equal likelihood on the entire map. So this is something which requires only local knowledge. You do not even need to know how large the set is, but eventually you will always convert to the uniform distribution. It's a very powerful result and forms the backbone of most Markov chain Monte Carlo algorithms that use a finite space. So here is just a final puzzle which is interesting in the sense, so far we see how to generate from the uniform distribution. You can actually generate from any distribution using the so-called Metropolis Hastings flip. It is a very simple thing in the following way. Suppose now the same map, but now I have certain numbers, certain labeling numbers, some non-negative, well in this case integers, no need of integers, some numbers, some labels, 6, 16, 4, etc. And what I do is the following. I want to converge to a distribution which is proportional to these numbers. So I have written 16 here, so I want to be here with a high probability. I want to be here with a very low probability. It is just a completely arbitrary specification of labels, and I can always make a scheme such that I will converge to that in the following way. Same as in the last case, but now whenever you try to move from something to something else, you will take a decision. Suppose you are at 1 and trying to move to 6. So it is like those people who hop from one job to another job just looking for greater salary. So if you get an offer from a different company that actually gives you more salary, then immediately you will make the switch. So if you are trying to move from A to B and B happens to be larger, you definitely go to B. But if the new job offers a bit less salary, even then there might be some reason to move over there. Maybe there is more chance of promotion, etc. later. So you do give it some chance. So if B is less than A, you still move with probability B by A. So you flip a coin with probability of head B by A. If it shows head, yes, you move. Otherwise, you do not move. So you basically tweak it. So you are giving more incentive to move to places with high probabilities, but there is some chance of moving to low probabilities also, but not much. And then if you can just work out the math, and it turns out that this indeed achieves what we wanted to achieve. The limiting distribution will have probability proportional to the levels. So the lesson to learn here is that you give me any distribution that you have in mind, I can give you a scheme like this which will converge to that distribution. So there is a scheme. You do not have to remember this scheme or anything, but there is a scheme by which you need only local information. At every step, you just have to choose a direction, then find out what is the level here, find out what is the level at the proposed point, and you decide. And if you keep on doing it a large number of times, you are guaranteed to generate an observation from that target distribution. This is a very well-known technique. This is called the Metropolis-Hastings technique. So all these four things are basically a crash course of MCMC that we need to know. Okay. So now we come back to our original problem of the 2 by 2 table, or in this case I have taken 2 by 3 table. The technique works for any m by n contingency table. So the idea was I want to inject randomness bit by bit. So here I have a contingency table. I want to tweak the entries such that I get a fresh random contingency table. And I have to remember that when I do so, I have to be careful because I must make sure that the total numbers here remain the same. So the same mothers and same children, you are only changing the pairing. So if I change, for example, the 23 randomly to 20, I must make sure that I have to, so I have reduced it by 3, somehow I have to adjust that 3. Otherwise, this sum will be different. So I have increased that 34 to 37. Of course, you could have added something here, 2 here and 1 here. Similarly, you have to make sure that this sum is the same, and you should make it 34, but just by mistake I have written 33. And similarly, this 3 has to be reduced so that all the sums remain fixed. It should be 34. So any such tweaking, you can easily understand, is nothing but adding a tweaking table, so to speak. And the tweaking table must be such that sum of all the entries in a row must be 0, so that the row sums do not change. These sums must also be 0. And when I do not write anything, you understand 0 here. So basically, you take this, add this, and get to this new table. So the idea is we want to do this randomly. This is my original table, and this is one random table that I have created, and I want this to follow certain distributions, etc. So that is the main idea. And as I said, all the marginals must be 0. This technique can be used coupled with that Markov-Chain Monte Carlo technique using an idea called a Markov basis. Still not Grobner basis. Oh, 45 minutes gone, still no Grobner basis in the talk. Terrible. So Markov basis, I will give the definition slowly. The first step is, it is a bunch of tables, all of the same size, in our case 2 by 3, with 0 marginals. So these are the things that we are going to add to our table so that we can generate new tables. Finitely many of them, here is one example. Some tables, all of them have 0 marginals, all marginals 0. So a Markov basis for the time being is just a finite collection of tables with 0 marginals. Certain other conditions are going to follow in a moment. So how am I going to use it? This is the idea. You have the Markov basis. So you have a collection of tables. Suppose you have got all these 0 marginal tables stacked up. This is the particular table that you have got from your data. So this is your observed thing. Now the technique is you randomly pick one of those cards and add it to this. So you get a new table, you can add or subtract. So you can flip a coin. If it is head, add. If it is tail, subtract. And then you get a new table with the same marginals. And you go on doing this. Let's just see an example. Suppose I pick one card at random, which happens to be 0, -1, 1, 0, 1, -1. This is one of those cards. I picked at random. If there are 4, I give equal probability to each of them. And I have chosen randomly to use, I'm just going to add. I can add or subtract. So the new table is this. So it is just like choosing north, south, east, west and moving to the next position. So this is my current table. I moved along this direction, came to this table. I added, so 5 became 4, 25 becomes 26, 3 become 1, 34 becomes 35, etc. Now what do? Okay, I again pick one of those things at random. Maybe I pick this one again, and I try to move. Okay, suppose this time I pick another one, which happens to be 3, 0, -3, -3, 0, 3, and I have flipped my coin. I have got a minus sign. Okay, I will try to move. Now I notice that there is a problem. I have a 2. Subtract 3, you will get -1. That is not a valid contingency table. I always need a valid contingency table with those original marginals. If I subtract, then I will get a -1. That I will not allow. So this is just like I am trying to move north, but there is no road leading to the north, in which case I just remain stuck wherever I am. So in this case, I remain stuck. I do not move. So this was the proposal, but I see I cannot accept the proposal, then I will step out of the space of valid contingency tables. I do not accept it. Okay, so I have lost a turn. Now I again pick one at random. Well, in this case, I happen to pick the very first one again. Same thing may occur any number of times. Okay, this time I have chosen minus, and you will go on like this. So in this case, you can do it. So it will be 3, etc., etc. Actually, you will go back to the original table in this particular example. So is this idea clear, what we are doing? We have a bunch of things, a finite set, and in this way, I want to generate one random table, step by step. Pretty easy to do using a computer. This is just some finite set of finite set of tables, and that is called a Markov basis. Now, based on our puzzles, we already know that this will work provided we have a guarantee that we can move from any table to any such table with the same marginals using only these steps. The same idea of if the city map is a connected thing. If you are stuck, you can never move from here to there using only these steps, then of course this randomization technique is not going to work. We needed the condition of everything must be connected. If we put that, we will get the precise definition of a Markov basis. So the precise definition is, we already know it's a bunch of tables, finitely many tables with 0 marginals. The totals are all 0. Now, the other condition, slightly less trivial condition, it should be possible to move from any table to any other table with the same marginals via valid tables. Any contingency table to any other contingency table with the same marginals, valid tables means in the intermediate steps, you should never get negative entries and things like that. If it is always possible, then you call such a bunch of tables a Markov basis, and based on our puzzles, we immediately see that using this, we can generate any distribution on the set of all contingency tables. You just go on throwing, you just pick on of one card at random and just make a move. So once you get a Markov basis, you can generate from any distribution over the space of all contingency tables with those marginals. So the important question is, how do you get that Markov basis? You said, if someone gives me such a nice bunch of tables such that they satisfy these 2 conditions. This one is a trivial condition, but this does not look like an easy condition. How do you figure out? Using only these 4 tables, you can move from any contingency table to any other contingency table with the same marginals. How do you design such a Markov basis? And that will give rise to Grobner basis. So imagine that this talk is divided into two different parts. The first part is over here. Keep this idea in mind. If somehow we can find Markov basis, our problem is solved. Now we move to a completely different world. And we will start to see what Grobner bases are, because these are somewhat advanced algebraic tools, not difficult, but there are actually various ideas that are built up to that. So I will give you a quick rush through all those things. I start with a very simple puzzle that all of us have solved as kids. The puzzle goes like this. You are given two containers, one measuring exactly 4 liters and another 6 liters, a huge container containing lots of your favorite liquid, whatever liquid you prefer. For me it is milk. And there is an empty container. These are not graduated, so you can measure only 4 and nothing else. You cannot fill it exactly half or things like that. The question is how to measure exactly 14 liters. How can you measure it? Anyone? Okay, you immediately say, oh, it is 4 plus 6 plus 4. So 4 and 6, 14 liters. Very simple. Okay, so that was the first one. How do you measure exactly 2 liters? Okay, you pour 6 and then take 4 back. What remains is 2. Good. How do you measure exactly 5 liters? Statisticians always like averaging. You take average. How do you do the averaging? How do you measure exactly 5 liters? Using 4 and 6. This was tricky.
Impossible.
Impossible? Why?
You can always have some even number.
Ah. He says that you cannot do it if it is not an even number. And why is that? Because since you cannot do any fraction of these things, all that you can do is take 4, put 4 or take back 4, or put 6 or take back 6. You have to only add or subtract 4 and 6. These are both even numbers. Howsoever you add and subtract, you can never get an odd number. So, not just 5, no odd numbers are possible. Is it true that all even numbers are possible? For example, 200 liters, can you do 200 liters? How?
6 minus 4 is 2, so...
Right. So since we know 6 minus 4 is 2, just go on repeating this 100 times. Pretty boring. I am not saying this is the most efficient way of doing things, but you can achieve it. So we learn a very important lesson here. And the main idea is this. Suppose we have only containers measuring these things, N1, Nk, some natural numbers. In our case, it was 4 and 6. Then we can measure only amounts which look like this. A1, N1 plus ... Ak, Nk for integers Ai's. This means if Ai is positive, you use that container A1 times to pour, and if A1 is negative, you use that container to take away A1 times. And you cannot do anything other than that because you cannot use fractions or anything. So these are the only possible things. That's the first set. Fortunately for us, we have this nice characterization. If both the numbers are even, then the resulting thing must be even, which can be written in this way. If I consider this set, those of you who love algebra might recall that this is called an ideal, no need of that term, but set of all possible things that you can measure, that can be expressed as multiple of the GCD. 2 here played the role of the GCD. Both the numbers are divisible by 2, so whatever you do by combining, you can actually do it using 2. Oh, I should have used this, I am using my hand. Anyway, okay. So this set, though it looks pretty complicated, actually is nothing but all multiples of the GCD. Is that idea clear to everyone? In our example, the GCD was 2, so all multiples of 2 are precisely the things that we can measure. So we reduce these things to only the number G and just look at all the multiples. That gives you a very simple way of describing things. So the idea was this, that you were given some containers, some integers, N1 to Nk, and you are also given a particular amount to measure. So in our example, it was 4 and 6, and this was say 5 or 14 or whatever. And the question was, can you measure n using these containers? That is n of the form summation ai ni for some integers ai, and you are to give an answer yes or no. And then the scheme that we use is the following. We first compute the GCD. There are so many ways of computing the GCD. The standard way is to use just Euclid's algorithm. You use Euclid's algorithm, say that is that long division technique of finding the GCD. You find that and keep it, and just keep it with you. So when I gave 4 and 6, you remember GCD is 2. So GCD or HCF, by whichever name you are familiar with, you just remember the number 2. Now whenever someone gives you any n, you just divide that n by the 2 and see if it divides, you say yes, it is possible. If it does not divide, you say no, it is not possible. So this is the general way we can do it. Now mathematicians have a habit of generalizing everything, and there is good reason why one would like to generalize it. Indeed, the need for weighing liquids is not a very valid practical reason why people worry about these things. Anyway, so for this technique, to generalize this technique, we notice that there are two things to be generalized here. Number one, we needed a way of finding the GCD, Euclid's algorithm. We needed a way to check divisibility. If we have these two things, you can always solve the problem. Now mathematicians tried to generalize this to polynomials. Why? There's a lot of story why people could care about this. I am not going to go into that story. Suppose I give you a polynomial. I have given you something 3x to the power 10. The 0 should be up there. It has come down. Sorry. So for example, polynomial is something like that. Some numbers, real number, x, then just x to the power some power. Here I have given all the coefficients to be integers. They can be any real numbers, but the powers, of course, has to be non-negative integers. Again, the same question. I give you some polynomials, not integers anymore, and I give you a polynomial here. The question is, can you express this polynomial as a linear combination of these? That is summation ai pi, where the ai's themselves, by the way, are polynomials. And I want the answer, yes or no. Turns out that this question has exactly the same answer as that elementary puzzle, and the technique is same. You find out the GCD of the polynomials using the same Euclid algorithm. We remember how you find out GCD of polynomials. You just divide long division, take the remainder, then divide by the remainder, etc., etc. The same algorithm, it will give you the GCD. And again, given this polynomial, you divide by the GCD, see whether it divides. If so, yes, otherwise it is no. Exactly the same proof, same thing goes, except that the GCD is now a polynomial, and here you have to carry out long division, the thing that we learned at school. Okay, because of some reasons, mathematicians tried to generalize it a little bit further. But before that, let's quickly recall the long division algorithm, because we will need that in a moment. This is the thing that we learn and generally hate at school. So you take one polynomial and you divide by another polynomial, you get a quotient and you get a remainder. How do you do it? You first write down all the terms in decreasing order of power. Here is the divisor. You try to knock off the first term by a suitable multiple. I have to multiply it with 3x squared. I write that here. 3x squared times this, 3x cubed plus 9x squared. Subtract, knocks off. This is x squared plus 5x plus 8. Now you plan to knock off this, multiply it with x. Now you are left with this, you knock off this, and finally you are left with this number. In general, it will be a polynomial of degree less than the divisor. So that is the way we carry out long division. We will need that when you generalize, so that's why I just reminded you. So when I say that G is GCD of a bunch of polynomials, basically we mean this. A polynomial P can be written in this form if and only if G divides P. So that is, I can say, that is actually the definition. Of course, we typically in school define it in a slightly different way, but it is actually the equivalent thing. This is GCD means you can write something in this form if G divides P. Now we will try to generalize this for multivariate polynomials. Multivariate polynomials mean there are more than one variable like x and y. Here is one example. Suppose P1 x and y. Of course, x and y both may be present. In this case, the technique just fails. You cannot use that technique. You cannot even define GCD. For example, what is the GCD of this polynomial and this polynomial? This polynomial is just x and this polynomial is just y. What is the thing that divides both x and y? They are variables, only constant terms, nothing else. So you might be tempted to say it has to be 1, but it cannot be 1 because 1 itself cannot be expressed as a linear combination of x and y. So there is no GCD at all of these two polynomials, and there are so many polynomials, multivariate polynomials for which you cannot even define GCD. So that prescription of checking whether something can be expressed as a linear combination unfortunately falls flat. Now a gentleman called Grobner, now I have come to Grobner finally, he had an idea that we should be able to generalize this, Euclid's algorithm and all those things, even for multivariate polynomials. He had some idea. He worked on it for 16 years, could not prove anything. So he did not succeed. And famously, after some dinner, one of his colleagues apparently had told him that I believe that what you are thinking is true is actually not true. And Grobner had answered, yes, I believe so too, but I need a proof before I accept it. Now this gentleman, Grobner, had a student, Bruno Buchberger, and he gave him this problem. He was his PhD student. He gave him the problem, can you come up with a method by which something like a generalization of GCD, the same idea of Euclid's algorithm, that will work for multivariate polynomials, but did not give him any hints. He did not tell him that I have been working for so many years on this problem. It is just a fresh problem. You try. Buchberger came up with a wonderful solution. He generalized the idea of GCD. The only little thing that he had to change was GCD is no more a single polynomial. It is a finite set of polynomials. And in honor of his advisor, he called it a Grobner basis. It is just a generalization of GCD for multivariate polynomials. Now when you look at the theory, you will see, oh, it is so nice and so simple. Why he could not get it for 16 years? But now we are looking at it with the benefit of hindsight. So the first thing that we will have to do is to see how we generalize that long division algorithm. And the generalization that I am going to show is more or less a trivial generalization with a little subtlety. And once you see it, you will immediately see how to do it. Suppose I am going to divide a polynomial, a multivariate polynomial, in two variables using not just one divisor, but a finite number of divisors. So I am generalizing the usual high school way of dividing in two ways. Number one, each of my polynomial can have more than one variable. Number two, there are simultaneously more than one divisor. So you write them down like this. Since there are two divisors, I have put a separator, and this is divisor 1, this is divisor 2. There are going to be two quotients obviously, so I have put a separator here. The thing that will be the quotient for this will be written here, the quotient for this will be written here. And I am starting. Now first of all, how am I ordering the terms? Here it is difficult. There I just ordered them using the powers. But here it is difficult. This is power 2 and this is 1. This is 1 and this is 2. Which one should come first? There are various ways by which you can write it down. A simple way is always write in decreasing powers of x. If there are two things of the same power of x, inside them you order them according to decreasing power of y. So here power of x is 2, that is the highest. I have written it first. Here power of x is 1, it comes next. Here power of x is 0, so it comes last. I have just ordered them according to x. Had there been two x squared terms, I will write the one with higher power of y first. You can have actually done the same thing starting with y, that is irrelevant. You fix one of these orders and you just follow. So what do? My plan is simple. I want to knock off this fellow and I want to knock it off with this. So if I multiply xy using x, I can get x square y, write it down, subtract, and immediately I have written it in the quotient term for the first one, so I have written above the separator. So this has been knocked off. My remaining terms are this, this, and this. Observe how am I writing. X, y square is written first. Then I write x, because power of x is the most important thing. Both of them have the same power of x. Within them I am ordering by the power of y. Y square, then y to the power 0. This has no x, so this comes last. So I always fix this order. So now my next thing of attack is I want to kill this fellow. I can kill it using either this, by multiplying this with x, or multiplying this with y. Since I have written them in this order, I will always give this fellow a preference. If I can use this, I will always use this first. So I multiply this with y, xy square minus y. Subtract, you get this. Now, so far it is a more or less simple generalization. Now comes the tricky part. The tricky part is this x, which is the first term here, cannot be knocked off by either xy or by y square. What do I do? In case of univariate thing, I will stop and declare this as the remainder. Not so in this case. I have still hope of knocking other terms. So what I will do is, I will take this term and say I will put this in the remainder. Look at the remaining thing. Y square in the next in the line. Y square can be knocked off by this. So I will try to knock y square off. I am multiplying this with 1, so I write 1 below the separator. Y square minus 1, use the subtraction. Now I am ending up with y plus 1. I plan to knock off y. Y cannot be knocked off. So I put that in the remainder. Next I try to knock off 1. Can't knock that off. I put that also in the remainder. And now my algorithm is over. So in this case, I get quotients and I get the remainder, which is x plus y plus 1. This is called, you can call it long division, but the standard term is polynomial reduction algorithm. Just a straightforward generalization of the long division algorithm, except that here I am working with polynomials of more than one variable and multiple divisors. So this was the algorithm that Buchberger used, and he came up with Grobner basis. He said that this is the thing. Let P1 to Pk be multivariate polynomials. Consider the set of all polynomials that you can write. So that is all the volumes of milk that you can measure, where ai's are just any polynomials. Since they are called ideals, I have used the notations I. The question is, given a polynomial, whether it is of this form or not. Then he said that you can compute the GCD, except that it is not a single polynomial anymore, it's a finite set. Even if this is an infinite set, this will always be a finite set. And I have a little typo here, this k does not have to be this k. It can be just anything, and this can be just any. This has to be always finite, this may even be infinite. So you will get a particular subset that plays the role of a GCD such that our standard property holds. A polynomial is of this form if and only if this set divides P. That is, this set, if I divide, remainder will be 0. And he showed the existence as well as a generalization of Euclid's algorithm by which you can actually compute a Grobner basis. It's not a very difficult algorithm. There are lots of implementations of that and lots of variation. There are a lot of research about making it more efficient, etc., etc. And many standard software packages, many of them are free, already compute Grobner basis and carry out the polynomial reduction for you. This is the very simple operation when you are using a computer algebra system. You can use Maxima, which is free, or you can use Mathematica, which is pricey. So the main idea is this, exactly the same thing that we did. I give you some multivariate polynomials and also a fresh polynomial. And I ask you, can you express that as a linear combination? And the technique is simple, that you find the Grobner basis and you divide by the Grobner basis and see if the remainder is 0 or not. Unfortunately, this is not unique, but you can make it a reduced Grobner basis if you put this extra condition. I have just written it for completeness, no need for this particular talk. If no GI, no element can be reduced by the other elements, then you call it reduced, and the beauty is this is unique. So given any such I, There is one and only one reduced Grobner basis, and computers will easily just compute a reduced Grobner basis for you. So what do I get? So this is the thing that you have to remember from all this Grobner basis thing. Same old story. You are given a bunch of multivariate polynomials. These are like the volumes of the containers, and also a target volume, a target multivariate polynomial. Question: can you write P as a linear combination of this? Now the answer is apply Buchberger's algorithm, which is the generalization of Euclid's algorithm, to compute Grobner basis, which is the generalization of GCD, and then check if this divides P, that is, whether it reduces P to 0. If so, say yes, you can. If not, you say no, it cannot. So the very simple high school thing can be generalized even for multivariate things. And that finishes why so all the things that you really need to know about Grobner basis. Now remember, we had left our story about Markov basis. We said we had contingency tables, and we want to move from one table to another. And then he said, if we can get a Markov basis, then life will be simple. If you still remember those things. The point is, Grobner basis will actually give you a Markov basis. I am not, of course, going to prove it. I will give you the reference. The proof is not at all difficult. You will not need, say, more than half an hour to just read and understand the proof. It's nice and neat, but we do not have half an hour, so I will not go into that. I am straining your patience already, apparently. So I will just tell you how it is done. So suppose I start with a table. So this is my contingency table. It is in this case 4 by 4. These are the marginals. There is no multivariate polynomials at all in the problem. Why? How am I using multivariate polynomials? Well, for each cell, you assign a variable. I have named them conveniently. So if the ij cell has a variable called xij, we just associate a label. You just associate a variable with each cell. They are not the frequencies or anything, just some symbols. For each row sum, I have associated a variable which I have called R1, R2, R3, R4. For each column sum, I have associated CIs. I have not associated anything with the grand sum, just the grand total. Now I will create certain polynomials. This just looks like magic. It is magic. So whoever thought about it for the first time, I think it was Percy Diaconis and Stamfels. I do not know how they really got the idea. I once asked Percy. He just said it just occurred and things like that. And anyway, he is a magician. He actually never divulges his secrets. So what you do is you consider all polynomials of the form xij minus ri times cj. So x32 minus r3 c2, x11 minus r1 c1. So you get, in this case, 16 such polynomials. Very simple polynomials, just binomials actually. They have a nice form. The form, I have given the name, this is not a standard name, disjoint difference form. In the sense, you see there's a difference, something before the minus sign, something after the minus sign, and they are disjoint. No variable that occurs here will occur here. This is made up of only x, this is made up of only r and c. So I call it disjoint difference form. This form is of some importance. So you get, in this case, 16 such things. In general, you get mn such things. You just find reduced Grobner basis. You fit them in a computer, find the reduced Grobner basis of all those 16 polynomials. It will take hardly a fraction of a second, and you'll get this. You will find, it can be proved, though that paper does not really prove it, they just assume it, but it can be proved, that all the things that you get will again be of the disjoint difference form. If you apply that algorithm, you will get, if you compute the reduced Grobner basis, you will get of the same form. That is, just difference of two things, whatever occurs here will never occur after the minus. And that will give you a Markov basis. So let's see an example. So I am showing using the software called Maxima, which is a free software you can download. And then you write load Grobner. It's just already there. It's one of the add-ons. You do not have to download it separately. And you write down all the things. So x11 minus r1 c1, x12 minus r1 c2, etc., etc. All the 16 things. I just wrote a little I just wrote a little program to create this list for me. And the command is poly reduce Grobner. So all functions in this package are called poly underscore reduce Grobner. And you give a list of all the variables that you are going to use. If you do not mention that, it will think that whatever is not mentioned is actually a constant. You tell them that consider all these things as variables, hit enter, and in a twinkle of an eye, you will get a list of all the polynomials in your reduced Grobner basis. All these things are the things. Look at the entire list. You will find first there is a bunch of them that involves R's and C's. Scrap them. You do not need them. So it is just like a magic prescription. You throw away all the polynomials in the reduced Grobner basis that involves the R's and the C's. Look at all the things that involve only the X's. In this case, I can find that there are 9 of them. The number could change depending on Amen, etc. So you get these things. All of them have the disjoint difference form. Let's look at this. It's difference of two things. x12, x31. You see x12 will not be here, x31 will not be there. Similarly, x11 is not there, x32 is not there. So you get some polynomials. But we need certain tables that add up to 0, marginal. That will be our Markov basis. How do you get Markov basis from that? You do it in the following way. I will decode it. So let's take one example. Suppose I take this fellow, x22, x31 minus x21, x32. From this, I will decode it in the form of a table. We are working with, in this example, 3 by 3 tables. So I will take x22, position 22, 2, 2, write a 1 here. 3, 1, 3, 1, write a 1 here. So you have exhausted this. Now come to the thing after the minus. So there it is x21, x21. Because it is after the minus, you write a minus 1 here. 3, 2, you write a minus 1 here. And nothing else, so you fill them up with zeros. So you get a table with 0 marginals. And in this way, you get one table from each of those polynomials, guaranteed to be a Markov basis. That's just a magic. Why should that be true? Okay, I'm not actually going to explain why that should be true. As I said, I'm going to give you the reference why that should be true. But what I will do is, I will just illustrate how you can generalize. That is, this is only for tables, and I have told you right at the beginning that this technique may be very impressive, but for our simple problem, the simple idea of randomization, making the mother stand in a line and randomly permute all the children, that is a better solution. That is a far more efficient solution. However, this one can be used in many, many different situations. So here is the general setup. That's my last slide. Yeah.
Why you wrote that 1 means 1 minus 1?
Why I did it? Okay, so let's just see. So I said that I want to get a Markov basis, right? A Markov basis consists of various tables such that the row sums and column sums are all 0. Here I have ended with certain polynomials. I have to convert these polynomials into such tables. And the way I am doing it is this. Suppose I pick something, say x12, x23. Suppose I am x12, x23 minus x13, x22. x13, x22. I want to convert this into a table, 3 by 3 table with 0 marginals. And this is the way I am doing it. You first write down a 3 by 3 table. And the positions are 1, 2, 3, 1, 2, 3. You look at these things. These will dictate where you put plus ones. x12, 1, 2. This position, you write a plus 1. 2, 3. You write 2, 3. You write a plus 1. So everything before the minus will put plus 1s. Everything after the minus will give minus 1. So that is the prescription. x13, x13, minus 1. x22, minus 1. And fill the remaining entries with 0. So this polynomial gets translated into this table. Okay?
Suppose if you will put like 10, 10, that will also satisfy that condition, like 10 or 10.
If you put 10, yes, that will also satisfy, but if you put that, that need not be a Markov basis. Because it is quite possible that you may not be able to make a step of size 10 from some given table. Okay? So this gives you one possible Markov basis. I am not claiming that this is the only possible Markov basis, but this gives you one possible Markov basis. Okay? So if you put 1 minus 1 this thing, then you get one possible Markov basis. It is possible that even if you put something like 2 minus 2 minus 2 1 or something more exotic, even that is possibly a Markov basis. But this gives you one Markov basis. Okay? So that is the scheme. I have not justified how did I know that I have to put 1 or minus 1. That is sort of part of the statement of the thing. Okay? That is the thing.
Sir,
yeah.
There will be total 9 steps here.
In this case, there are total 9. But this number will actually change if your, say for example, size of the thing is, say the size of the tables are different. In this case, it is this. But what is guaranteed is, you will always get this disjoint difference form. That is guaranteed. Okay. So this is the general setup where the same thing can be used. I just gave this as one example in terms of contingency table and just checking for lack of association. So here is the general setup. You start with any exponential family with this PMF. It looks complicated. I'm just trying to impress you that it can be worked with in a more complicated situation. So script X is a finite set. So in our example, in our very first example, our script X was this set. It was this set. It has only 4 entries, world, world, both mother and child has world, world, no world, no world, world, and no world, no world. So in our very first example, script X was these 4 possibilities. And the thing that I said there is no association, that was a model of this particular form. That was a very trivial model of this particular form, but there are many, many complicated models, all sorts of log linear models, etc., can be couched in this particular form. So suppose you have an exponential family with this PMF, and you have some data, IID, x1 to xn, IID with this PMF. In our example, we had n was 207, we had 207 families, each one of them landed in one of these 4 cells, so their IID with this PMF, then a standard result of exponential family says that this sum will be a sufficient statistic. That's just a straightforward thing. And then this Grobner technique that you have learned can actually simulate from any distribution over this set. Look at all, so you're essentially conditioning on the sufficient statistics. I hold the sufficient statistic value fixed at the given value t. Look at all the possible tables that you can get, all the possible types of samples that you can get, which gives rise to this sufficient statistic, and whatever distribution you have. Whatever distribution you have, you can actually generate using the Grobner technique. So this is in its full generality. Of course, this can possibly be generalized even further, but at least the paper that I am sort of presenting, that ends here, and the example that we saw is one particular example. So that is the very last slide, and anyway, I'm going to share this. So if you're writing, you can already have this soft copy. So if you're interested in reading further, and I hope you will be interested, I am just trying to whet your appetite that there is something nice out there. First of all, this idea of Grobner basis, someone tries to generalize GCD. So this GCD is so very old thing, and someone actually trying to generalize in the modern times, and also how to use it in statistics. This is one possible application. There are some other applications in design of experiments, etc. So this is the paper from which I actually presented this technique, and they give you some generalizations, etc. also, Diaconis and Sturmfels. I would not call it a very readable paper, but there are actually examples, etc., but not very readable. But if you are really interested in learning about Grobner basis, this book is a wonderful book. It is a wonderful book, Cox, Little, Oshie. Unfortunately, they do not talk about application of this in statistics. They do talk about applications in lots of other areas, But this is a wonderful book and a very friendly hands-on introduction to the subject. So the main aim of this talk was just to get you excited. There is something new, something fresh, and even if no new PhD comes out of it immediately, at least you can do master's project and things like that. That's a very nice, exciting topic. Okay, that's it. Thanks for your patience. Finished on time. Okay.
This is a really wonderful talk, and